This project, we will be designing and implementing a programmable square wave generator. In the domain of digital systems and embedded design, achieving precise timing control is important. While fixed frequency clock generation is straightforward, applications like pulse width modulation and custom protocol timing demand a signal source that can change dynamically. This necessitates the development of a programmable square wave generator. Our project focuses on the design and Verilog implementation of a fully synchronous programmable square wave generator on a field programmable gate array. The key innovation is the generator's ability to produce a square wave with independently variable on and off intervals. These durations are defined by two independent 4-bit control signals M and N. Interpreted as unsigned integers, these signals directly set the pulse widths in nanoseconds, utilizing the 10 nanosecond period of the onboard clock. The system is implemented on the Z board using the Xilinx Vivado design suite, leveraging the FPGA's inherent advantages of high speed and precise timing control. The main objective of this project is to successfully design, implement, and rigorously verify the programmable square wave generator circuit on the Zinc Z board. We have five core specific objectives: design and control, develop the robust synchronous circuit with independent on and off time control using M and N inputs, and integrate and enable functionality for precise gating of the output. Platform implementation. The logic is captured in Verilog HDL for efficient utilization of the FPGA's resources. We use Vivado VIO to supply the dynamic control signals and a dip switch for the external enable input. Verification. Our most crucial objective is to verify the operation using the Vivado Integrated Logic Analyzer ILA tool. We perform real-time on-chip validation by tapping the control inputs and output and a special 20 nanosecond reference clock. This allows us to accurately validate the generated square wave's duty cycle and frequency against the desired values.
Hello everyone, my name is Adi and I'll be explaining the design code and the test bench for our project Square Wave Generator. So in this basically we have taken the clock reset which is active low, enable which is active low, input wire of size 4M and input wire of size 4N, and the other three are outputs: square wave wherein the output comes, and ref clock def is just the output wherein the clock gets divided by 2. So basically M and N signify the the amount wherein the clock stays high, and N signifies the time where the clock stays low. So as you can see below, we have assigned a variable on cycles as M and assigned off cycles as N in order to maintain understandability in the code. And as we can see down in the first always block, and we are just dividing the clock by 2, wherein only at the positive edge of the clock is getting triggered. But now as we can see, now as we have divided the clock by 2, now if the reset is set to 0, the global counter and the on state and the output all three become 0. And in also if the reset is not low, and if the enable is low, the counter global counter sets to 0, and the output also goes to 0, and this on state is also set to 0. But if the enable is high and the counter is set to 0, we can see that the clock is we can see that the we have achieved the required output of keeping the clock high for m seconds, and then that is why we trigger it when the counter becomes 0. And else if it is in the off state, wherein the state on is equal to 0, so in that we trigger the output to 1. And at the end, after each iteration of the always block, we decrement the counter by 1 in order to maintain the global count for it. And now as we come on to the test bench, we can see that we've already declared the wires in the code as registers and the resistors in the code as wires in order for the test bench. And now we have initialized the design code in the test bench, and as in the first initial block, you can see that we have declared a clock with time period of 10 nanoseconds. And after that, in the first case, we've taken M and N both to be 0, and then after 50 nanoseconds the reset becomes 1, wherein the reset is not working, and the M and N both are set to 5 and 3. So basically this means that the clock will be high for 5 nanoseconds and low for 3 nanoseconds, and enable also becomes 1 here, and after 500 nanoseconds the high becomes the the high becomes 2 nanoseconds, and low becomes to 4 nanoseconds, M and N. And in the last test we can see that the M and N both equal in order to consider all cases. And that is it for the code explanation. Thank you.
This block diagram shows the complete hardware setup for our programmable square wave generator using Vivado IP integrator. The design is synchronized by 100 MHz system clock, labeled as clock 0, which drives all three major components shown here. At the center is the VIO block, or the virtual input output. This allows me to provide real-time digital inputs directly from Vivado instead of physical switches. We have used four VIO outputs. Probe out 0 supplies the 4-bit on-time value M. Probe out 1 supplies the 4-bit off-time value N. Probe out 2 is the enable control. And probe out 3 drives the active low reset. These go straight into the square wave generator, letting us program the waveform dynamically during hardware testing. On the right is the square wave generator RTL module. It uses the clock and the VIO inputs to generate a clean synchronous square wave with programmable on and off intervals. It also it it also outputs a reference clock divided by 2 signal, which is a divided clock used as a reference during verification and cycle counter, and a cycle counter that shows the internal timing state. At the bottom is the ILA, the integrated logic analyzer. This acts as an internal oscilloscope. I have connected all key signals to the ILA, M, N, enable, square wave, and the reference clock divided by 2. With these probes, we can capture the waveform inside the FPGA and verify that the timing of the square wave perfectly matches the programmed values. In summary, VIO provides live control, the square wave generator provides the waveform, and the ILA validates its behavior, all synchronized through the FPGA system clock. Next, we will demonstrate how this works out on our hardware FPGA board.
So this is our project programmable square wave generator. So we have dumped the code onto the FPGA board, and we are getting the VIO here and the ILA waveform here. So I will just set the M and N values. M is for the off time and N is for the on. So I will just give some values here. In our code we have coded such that we have to put enable and reset 1 for to generate a square waveform. So I've given, and here as you can see the clock is also changing and we are also getting a square wave, and we can right now I will trigger ILA waveform so that we can get a square waveform. As you can see, we have generated a square waveform which so here is the square waveform which starts from 1 till 6. So as we know, I have given M is equal to 5 and N is equal to 3.
So to conclude this experiment, we designed and implemented a fully synchronous programmable square wave generator on the FPGA. We used the 10 MHz onboard clock as our timing reference, which has a period of 10 nanoseconds. The on and off times of the output are controlled by the 4-bit inputs M and N, treated as unsigned integers. As a result, the output stays high for M clock cycles and low for N clock cycles, exactly as expected from the design. The enable signal correctly starts and stops the waveform, and the reset brings the circuit back to a known state. We verified all this on hardware using VIO to change M, N, and enable in real time, and ILA to observe the internal counters, the reference clock, and the output waveform. Now to the use cases. This kind of programmable square wave generator is quite useful in practice. First, it can act as a configurable timing source or test clock for other digital modules when we are prototyping in this lab. Secondly, it can be used as a simple PWM style generator to control LEDs or small actuators, where we can just need a coarse control over the duty cycle. Third, it works well as a stimulus generator. We can feed this signal into other circuits to test how they behave for different pulse widths and duty cycles. At the same time, there are a few limitations in this current design. Because M and N are only 4-bit values, the range and the resolution of the on and off times are limited. The output frequency and duty cycle are also restricted to integer multiples of the system clock. So we cannot generate very low frequencies or arbitrary duty cycles without modifying the architecture. Right now, the design produces only a single channel square wave and does not support features like phase control or multiple outputs. Finally, configuration through virtual input output or VIO is convenient for the lab, but it's not a user-friendly interface for a final product. These points highlights clear directions for future improvement of design. Thank you so much.